went off for a little bit.
No, it's okay. Okay, so good morning, everyone. And I think we continue now our session of contributed talks. And it's also my pleasure to introduce the next speaker, Gabriel Cunha. And today, Gabriel is going to talk about the existence of steady states for the Maxwell-Schrödinger-Poisson system by the concentration-compactness principle.
Good morning, everybody. I would like to, first of all, thank the organization for being so nice to me and accepting my request to speak for a little bit about what I've been studying for the last couple of months, at the Federal University of Goiás for my master's degree. My advisor is Professor Caio Oliveira da Silva, and it's a interesting problem, and it is a variational approach for a PD problem, for searching for weak solutions for a PD problem. And I am going to talk briefly about the variational approach here for the problem, and then go to the main topic of this talk, which is the compactness problem, which is the harder problem. So the problem I study is this, right? It's PD here. As you can see, those functions, these functions here, they are complex functions, A priori, we have this self-consistent Poisson potential, which is not determined yet, but we will determine it later on. So we are going to seek for solutions of this form. They are called standard waves solutions, right, to the problem. We are going to seek solutions for E equals to 1, which comes from this constant comes from the applications, the physical applications. So E equals to 1 is the repulsive case, and E equals to -1 is the attractive case. So we are going to look for solutions of this form where this complex exponential, and this is a real function. Phi is a real function. So as you can see, in this case, for each fixed t, positive t, we have a different standard wave for the problem, right? So, so if we substitute this function in the original PDE, we get this version of the PDE. It's basically putting this function there and canceling this constant, which will appear on both sides of the equation. So using this very important theorem here, we can show that this PDE is actually equivalent to this PDE, and this happens basically showing that the only solution we have for this PDE here in the weak sense is actually this function here. So we know. So what we do is substitute this function, this solution here, and we get this equivalent version here. This constant here suggests a usage of the Lagrange multiplier theorem for associated minimum points, as we will see very soon, with the weak solutions. So the way we solve this PDE is by using Lax-Milton theorem. So you guys, folks, are probably very used to using lattice medium theory. So I'm not going to talk much more about this, but it's basically showing that this functional here is bounded, coercive, and this functional is, this linear function here is bounded. Basically that. So we get equivalence. We know now that the problem we should be solving is this, right? So we are seeking for solutions in the subolet space. It'll be more clear why this space is very small. So if you multiply it, so I'm going to briefly talk about the weak solution, very briefly now. So if we multiply this PDE size for a function, function v on the subolet space, integrate using the green formula, we get this expression here. And as you can see, if you take this function on the subolet space, this functional, and we differentiate this function in the Fréchet sense, we get this expression here. So we take this function, which is called the energy function, and this term comes from the applications again, because very often this function is associated with some kind of energy. So we this minimization problem, right? So this is the trace of the L2 the Lebesgue sphere of ratio R on the subolet space, as you can see, right? So we look for, so notice that if we take this function, so this phi that you see here, it is the function that determines, is this integral minus R. So it is this phi here. So by the Lagrange multiplier formula, if we can minimize this function on this sphere, that formula says that this equality holds. So in particular, for OV in the subolet space, this equality holds. And if you open up this expression, you see this expression to 0, which is the definition of weak solution. So this was only a brief explanation of the variational approach, the definitions. Right? Everything has to start off by the basics. So our problem is a minimization problem. So what we do is, first of all, we study in what cases this infima is finite. Have some problems where we don't have to show this infima is finite first. We show it is reached by some function here, and then as a consequence, it's finite. But we would like to not waste our time trying to show that if this infima is reached in a case that might turn out not to be finite. So we first try to figure out what case this infima is finite. So in this talk, I'm going to discuss this case because it exemplifies the math pretty well, and especially how we overcome compactness issues here. Right, but as you can see, for some cases, this infima is less finite. Right. So for this particular case here, P, as you can see, comes from this. This is P, right? So I'm not talking about this later on. So the idea behind the variational approach is, well, we have an influence, so we take a sequence on this set called the minimized sequence, in a way that the numeric sequence obtained by the action of this function of this sequence is a numerical sequence that converges to the infinite. So what we do is to discuss the possibility of this minimized sequence to converge in some sense, in this case, the weak sense of the Sobolev space, for a function phi0 in the Sobolev space. We do that by showing that sequence is because the Sobolev space in this case is a reflective space. So we use the Banach theorem. And don't know if I pronounce them correctly. I don't know if my internet is okay. So this is kind of the easy part to show that the sequence, this minimized sequence converge. The problem is, do they converge to the restriction? Because if they do converge to the restriction, as I will show to you at the end of this talk, we are done. We have a function here such that this function acting on this function is equal to the infinite. Is a minimizer to the problem. This minimizer is called ground state. So not always the weak solution is a ground state, but in this case is a ground state. So so the way we overcome the compactness, which is the main topic here, the main point, is by using the really beautiful lemma to do the proper reference to the two papers on the reference at the end. And it is very interesting theorem. So as you can see, that if we have a sequence of functions in the ground space, which has constant mass, we use this term when we are dealing with compactness, concentration-compactness principle. The designer rho is the mass of the function. But again, it comes from the applications. So if we have a sequence like this, up to subsequence, one of these three options hold, and only one of the options hold. This first option here, this is the ball centered in U and I, this letter. So this is the ball centered at this I, and with radius T. So we take the supremum and the limit. So one possibility is if this limit is 0 for all possible. This case is called vanishing. So is the case where, as we will see later, all the mass is lost. So the second case is called, the third case is called dichotomy. So there is this constant here, such that for all positive epsilon, we can construct, starting from epsilon, taking these two functions. These functions depend on epsilon. These functions are in L1. Their support, they disperse from each other when the diameter is big. And these three relations hold. So in this case, you can imagine it, the mass function. If you think of the function as some lumps, some bumps. So what we are saying is that for n bigger, the bumps where the mass of the function, which generates the integral, they are coming away from each other. So in this case, so function doesn't necessarily lose the mass, but the mass dissipates. The nice case where we don't have that loss of mass. So it's a very nice case, as you can see. And we want to show that when we take a minimized sequence, the integral of the squared function, it has constant mass, which is the rate that we took before. And we want to show that this case cannot happen in minimized sequence, and this case cannot happen. So we have backwards. So I'm going to show how to do that briefly and how that is used to us exactly the. So the demonstration of this lemma is done by using the lemma for the so basically says that if you have a sequence of functions defined bounded and increasing up to subsequence, they converge pointwise to an increasing function in the compacted interval. Don't know if my internet's okay. So to prove the lemma of Leon, they define this sequence of functions. We show this of functions fit in the hypothesis of the Kelly's lemma, right? So we get the subsequence of the sequence converge pointwise to an increasing function, which we call k, right? And so since this function k is increasing, we can take the limit when t goes to infinity. And the three possibilities for the limit produces the three cases of the compactness lemma. So as you can see, essentially the proof of the lemma is not very complicated, although in reality it's quite difficult to make these calculations fit because it has a lot of details to take into consideration, although the math is not very complicated. So it's quite simple. So in order to show that for me, vanish does not occur, we use a second lemma. We are going to use the previous lemma to show that continuity cannot occur. So to show that vanish cannot occur, we did. So basically we show that the sequence is bounded. So UN will be the square the minimized sequence. I'm gonna show this in details later on. So what I do is actually show this inequality. Notice that for p between 2 and 3, this number is negative. So considering the norm of the Sobolev space, in order to treat boundedness, we only have to take into consideration the norm of the gradient because the other part is already on the restriction, is already bounded. So for p between 2 and 3, this number is negative. So if we assume by contradiction that this number goes to infinity, this whole thing inside this part here, it goes to 1. So this goes to plus infinity. And this will go to plus infinity. But it cannot happen because if this is a minimized sequence, it has to go to a non-positive number. We show that it's a lemma for in this study. So it is a contradiction, which means that the sequence is bounded. It's a bounded numeric sequence. So the minimized sequence is bounded, and up to subsequence, it converges weakly to a function of phi0 on the Sobolev space. So what I do is to use this lemma to show it does not occur. So basically, this is bounded now, and we take k equals to 2. So for all alpha between k and 6, because n3 is the dimension of the domain here, right? The Euclidean space. So for all phi in this interval, this goes to 0. It means this expression goes to 0. Let me check the time here. So this is a contradiction because of the if you look at the energy function, you can see this part is the only negative. So if this go to 0, this has to go to a number that is not negative. But here we showed that this number is negative. So it is a contradiction. So So dichotomy is a little bit more tricky to show, but it's basically to show a contradiction with this inequality. So we show this is called the concentration-compactness type inequality, or the subaddiction inequality. It is always the inequality always holds, but not always is strict. So it is one of the most complicated theorems in this study to show this strict inequality. It's very complicated to show. And of course, I'm not going into that today. So by contradiction with that, we show by some calculations that we can give an example of a number such that we find a number between 0 and r such that this inequality does not hold. So it's kind of tricky, but you have to use some scaling here, some changes of variables, and you can show the contradiction if we suppose that dichotomy occurs. And the way dichotomy, if you suppose that on if you suppose dichotomy occurs, you get these functions here. So, which is these two functions here. So we kind of degenerate the original minimize 6 between these two. We can do to the square and to the first power. And this inequality here comes from the other inequality that you can see on the plan. So as you can see, this inequality. I'm sorry for going up and down like that on this. So we get a contradiction if suppose that dichotomy occurs. I am finished. I'm almost finished. So the compactness holds. You know that the minimized sequence is bounded. I don't know, the internet is unstable. So you know the minimized sequence are bounded. So the translation about them. So since this sequence is bounded, it converges weakly to some function in the Sobolev space, which means it converges strongly in the locally, right? In the Lebesgue space for key between those numbers, okay? And so using this inequality here, so using this inequality here, as you can see, right? You can see the translation here. Using quality here, in the compactness case, we show that this holds, this inequality holds. This is equal to this because of the strong convergence, in particular the norm converges, the norm of the system converges to the norm of the limit. So in this is larger than this by the Lyon lemma. On the other hand, by Fatou's lemma, we show that this number is less than the ratio. So this sequence, by the sandwich rule, this number has to be this number if we send epsilon to 0. So we have shown that the weak limit is on the restriction, and we are done for life. So it is a very beautiful argument, as you can see. And some parts are a little tricky to do, but essentially the idea is not very complicated, essentially. So para finish up, we just use the lower semi-continuous property of the energy function. So since this function phi 0 is on the restriction, the infimum is less than or equal the action of the energy function of this function, which is less than this number by the lower semi-continuous, which converts to this number. So we are done, and we found the ground state. So I'm sorry for a little delay, 1 minute delay, and thank you for the opportunity again.
Okay, thank you, Gabriel, very much. Actually, you just finished on time.